Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Fatiha Alfisha binti Sobri. My matric number is AE180028. I am from Group 3 of BEB 31803 Electronic Communication System Class Section 2. Our group is going to present regarding the task 2, which is about the digital modulation and transmission. My group members are He Chi Yang, He Zian Chi, Nur Hazika binti Bustamam, and also Muhammad Nuruddin bin Johan. So now I will start with the introduction first. So, in professional environments, digital recording technologies are gradually displacing analog methods for recording most types of signals. There are some of the advantages of this digital communication, which is in digital system, all signals look similar and only have two possible outputs, either logic 1 or logic 0. So therefore it can be said that the noise immunity is less and not necessary to evaluate precise amplitude, frequency or phase, and etc. Next, due to the possible output of logic 1 and logic 0, it is easier to do the multiplexing process. In addition to that, the digital communication also introduces redundancy into the information in order to correct any error occurs. The main topic of this assignment is about to do the pulse code modulation PCM. PCM is a digital representation method for a sample analog signal. So in this task, we have been given a block diagram of PCM encoding and decoding of an analog modulating signal and also several scenarios to analyze and discuss the resultant recovered modulating signal.
This is the filler table for task 2. So there are 5 learning issues. Firstly, to determine the suitable method used in digital modulation to transmit data. So we found that PCM is the best suitable way to digitize due to the consistency and the quality to transmit and can be used when signal traffic is heavy. And then second, how is the data convert from analog to digital? So they undergoes 3 sequence. Firstly, sampling, next quantize, and then coding. Thirdly, we want to know how to reduce the quantization error of an ADC. So the idea is by increasing the number of bits and for each sample, quantization error can be reduced. So due to the difference between the analog signal and the digital value at each sampling instant from the ADC is known as quantization error. And then which method used to remove drawback of PCM? So PCM actually requires a large bandwidth. Overload occurs when the modulation signal changes by more than the step size between samplings. So in order to reduce the excess bits, it undergoes the quantizing process. So when the sample output is fed into quantizer, the redundant bits are reduced and the value is compressed. Lastly, what are the Nyquist criterions means to the sample data? So according to the Nyquist criterion, the sampling frequency must be at least twice as high as the highest frequency in the signal. So the idea is by including an anti-aliasing filter or low-pass filter before starting the ADC and sampling, this can prevent unexpected high frequencies from entering the system.
Good day everyone, my name is He Chi Yang and today I'm going to explain to you our group's brainstorming process in identifying the cause and effect of the MPRIMD output as part of the methodology. So in this PBL we are provided with the MATLAB block diagrams. So we are going to use the MATLAB block diagrams, construct them inside the MATLAB and check on their parameters and identify what causes the changes in the MPRIMD output. So among the parameters that we have identified that cause the changes are the sampling pulse signal with the oversampling and undersampling condition. And then next is the age type and the latch buffer input in the sample and hold component. And then it is about the peak and bits component, the parameters inside the encoder. And next, for the integer to bit and bit to integer converter, the bit order and integer sign will also affect the MPRIMD output. And next is also the analog filter design regarding the filter type and the bandpass age frequency. And lastly, there are other reasons such as amplitude and block diagram additions that affect the MPRIMD output as well.
So now I will be proceed to demonstrate the block diagram for part A. For part A, the sampling frequency is the minimum of the Nyquist, which can be said that Fs equals to 2Fm. From the given equation, we know that Fm is equals to 100 Hz. So since the Fs has to be twice of the M function frequency, so therefore the sampling frequency used in this task is in this part is equal to 200 Hz. So as can be seen here, this is the block diagram for 4 bits PCM encoding and decoding, while this is the block diagram for 8 bits PCM encoding and decoding. So now the parameter used in the continuous pulse generator, the amplitude is set to be 5, the period is set to be 1 over with the Fs, which is in this case is 1 over 200. For the sine wave, the amplitude is set to be 5 and the frequency is 2 pi 100. So now we would like to see the waveform for the PCM output for scenario 1. So now we zoom to see the. So as can be seen here, this is the PCM output for scenario 1, which is the Fs equals to 2Fm for 4 bits encoded. So now we would like to see the output for the modulating signal. So this is the output for the scenario 1. The blue line represents the input signal while the yellow line represents the output signal. Next, we proceed to demonstrate for scenario 2, which is the number of bits is increased to 8 bits. So we would like to see the PCM output. So as can be seen here, these are all the PCM output for scenario number 2, while for the output for modulating signal, these are the output waveform for the scenario number 2. That is all from me. I will pass to my friends. Thank you.
Hello everyone, so today we are going to simulate scenario 3 and scenario 4. So these are the block diagrams. Their settings are largely the same as from scenario 1 and scenario 2 for 4-bit and 8-bit, except in here we are going to define the sampling frequency as 300 Hz. So we go to here, continuous pulse generator, we change the period to 1 over 300 seconds for scenario 3 and scenario 4, and then we run with the simulation circuit. Okay. Then this is the output for the PCM for the 4-bit, and this is for the 8-bit. There's a bit of a transient at the beginning, so we take the steady state value at the output, and so we find the recurring pattern for it. Okay, then this is the M prime T for the 4-bit, and this is the M prime T output for the 8-bit. Then we zoom in to the steady state part, enable with the two measurements, signal steady state, and then check for max min for the amplitude values of the output for the quantization interval calculation. So after we have done with the MATLAB simulation, so here are the results for the PCM output display in the table form. So there are signal forms of the PCM display and also the output signal. Okay, they are all written in the report. So here I summarize it in the short way. So these are the tables for the PCM output for scenario 3 and scenario 4. So the first thing you can notice that every 1 over 300 seconds, the PCM output changes because we are using the sampling frequency of 300 Hz. Okay, then next, you can see that the first 4 most significant bits from PCM1 to PCM4 are the same for both n-bit scenario, regardless whether they are 4-bit or 8-bit. Then lastly, the PCM1, when the PCM1 output is 1, the integer is negative, and when the PCM1 output is 0, the integer is positive because we are using the sign option. Okay. Then after that, we can calculate the quantization interval by using the n bits to calculate the number of binary codes. Then we can obtain the number of increments by minus the number of binary codes by 1. Then we can use the amplitude from the signal statistic in the MATLAB simulation from the output signal. Then we can calculate the resolution, which is another name for the quantization interval. So here we can observe that the scenario 3 quantization interval is bigger than the scenario 4. Okay. Then after that, we can also do the calculation for the theoretical perfect output of M prime T, where the amplitude is assumed as negative 5 volt and 5 volt. So these are the calculations. So now I'm going to discuss about the observation in the output signal M prime T. Okay, so for in this case, the scenarios, they have the phenomenon of high sampling frequency, which is also known as oversampling. So from the M prime T outputs for both scenarios, So it is observed that the quantization interval is smaller when the sampling frequency increases, and then there are phase shifting, equilibrium point shifting, decrease in amplitude, and also changes in periodic wavelength. So the oversampling will help to reduce the noise and also the quantization as well. So that's all for my part. Thank you.
Assalamualaikum and good day, Doctor. So I will continue the explanation for part C, where sampling for MT is lower than minimum required according to Nyquist. So here is the system diagram which was created by using Simulink. The function generator is located on the upper left to generate a square wave. So the amplitude is set to 5 and frequency is equals to 100 Hz. And then the duty cycle is set to 50% to transform the square wave into a sinusoidal waveform. And then here another function generator at the bottom left generates a sine wave where the frequency is 200 Hz. So the outputs of these two function generators are multiplied and the result is sample signal, which is then processed by a low pass filter. Now, from the output signal, there will be presence of unwanted components in the reconstruct signal. Furthermore, some of the original signal frequencies may be lost in the reconstruct signal. Therefore, signal frequencies overlap due to insufficient sampling frequency. Hence, the aliasing effect is not possible to recover original signal by low-pass filter. Moreover, due to the overlap at one region to another region, signal MT is distorted.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nuruddin Mejohan and my matrix number is AE180041. So now I'm going to present about the part D, which we have to observe the recovered message signal at the oscilloscope when we change the value of the amplitude to 15 volt to an 0.5 volt. And then in this task, we just have to use the circuit from the part B and we are not required to change any settings and just follow the initial setting from part B. And then basically there are two systems here that we will discover the output, which are the first one for 4-bit encoded PCM and another one for 8-bit encoded PCM. And then we will go through to the first VM, which is by changing the VM to 15 volt. And then we just click the sine wave here. Okay, it's already select 15 volt, so we just click OK and we click the run button here. So this is for 4-bit encoded PCM, and then we can observe the peak voltage here that which is around 2.67 volt. And then after we do the comparison in the context of error, we obtain 82.2% of approximation error. And then we will proceed by changing the amplitude to the 8-bit encoded PCM. And then we just click here and then it's already select 15 volt. We just click OK, and then we will click the scope here. So basically this is the signals. So we can so the yellow one is the recovered message and the purple one is the amplitude signal. And then we just observe and we can obtain the value of the peak voltage from the right side of the screen. There is a 3.2 volt of the peak voltage of the recovered message. And then after we do the comparison in the context of error, we obtain 78.67% of approximation error. So we can say that the nearest value to the original value is the 8-bit encoded PCM, which it produces a lesser error. And then we will proceed by changing the amplitude to 0.5. And then we will click the scope here. So basically we can see that the signal here is quite different from previous previous signal, which the signal will step down or decreases at t equal to 0.02, and it will produce a repeated shape of signal when t is equal to 0.04. And then we will proceed by look to another output. from 8-bit encoded PCM. So we change again 0.5. So this is the final signal for part D, and then we can obtain the value of the peak voltage, which is around 0.28 volt. And after we do the comparison in the context of error, we obtain 44% of approximation error. So that's all for the activity D. Thank you.
Good day everyone, my name is Dacian Chi with metric number AE1X0099. Today I'm going to do a video presentation for the last question, which is how do we make sure the resultant output signal is similar to the input modulating signal when the signal changes to case 1 15 volt and case 2 0.5 volt. First of all, this is for the 4-bit encoder PCM. When the input signal changes to 15 volt, in this case we can apply a low pass filter after the input signal to decrease the amplitude of the input signal. In the MATLAB, we'll apply an analog filter design block with the setting set to low pass Butterworth, and the filter order we set to 8, and the passband edge frequency we set to 2 by 88 radians per second. Then after we run the simulation, we can observe that the input signal now it is decreased from 15 volt to 5 volt. Also, we observe the output signal. We can see that the wavefront is similar to the output wavefront in part D, with the amplitude ranging from 2.5 until negative 3.7. Next, for the 8-bit encoder PCM, similar to the 4-bit, we will apply also a passive low-pass filter after the input signal with the same setting. Then we observe the input signal. It is also become 5 volt, and the output signal is ranging from 2.9 until negative 3 volt, which is also similar to the output wavefront in part B. So for the second case, when the amplitude of the input signal will change to 0.5 volt, in this case we will apply an amplifier after the input signal in order to increase the amplitude of the signal. So in MATLAB, we will apply a gain block with the value set to 10. After we run the simulation, we can observe that the input signal is now become 5 volt, also similar to the output wavefront. For the output signal, we can see that the amplitude is ranging from 2.2 volt until negative 3.5 volt. So this one is for the 4-bit encoder PCM. And next, for the 8-bit encoder PCM, also we will apply an amplifier after the input signal to increase the amplitude. Now we can see the input signal is also have 5 volt amplitude, and also the output signal. So for the output signal, we can observe that the amplitude is ranging from 2.8 volt until negative 3.0 volt. That's all for the presentation. Thank you.
Okay, in conclusion, pulse code modulator or PCM is a useful tool that converts analog signal into digital signal and then sample and codes the signal and reconvert back into analog form for data transmission. And there are many ways to change how the pulse code modulation works, such as undersampling, oversampling, Nyquist sampling, and filter block. And each block diagram setting can be easily affect how the output signal will be produced. And the process of PCM is complex in a way that the settings for block diagram can be very wide and open-ended, but simple in a way that the conversion between analog and digital is easily understood in numbers. And then several ways can be used to improve the PCM, such as using band pass filter, increasing sampling frequency, and using amplitude modifier to restore the signal near to original. In conclusion, pulse code modulation (PCM) is a powerful circuit system that is valuable in digital signal processing, and more research and improvement can be done to enhance the signal transmission system, which benefit our daily life. Thank you.